This lecture will introduce one of the most important concepts in the entire finance studies, and this concept is time value of money. We will assume that we already determined cash flows and the interest rates that these cash flows will earn, and we will learn how to compare projects with different streams of cash flows arriving at different times. To be able to do this, we need to introduce and learn how to calculate present value and future value of cash flow or cash flow stream. We will discuss the concept of the net present value. And we will learn few formulas which will allow us to calculate present values of some special cash flow cases. The key challenge for today is we need to learn to compare cash flows at different points in time. Let's start with an example. Consider an investment which pays the following cash flows at this period of time. So at time 0, today, we need to invest $1,000, and then for 4 periods after that, we will receive $250, $350, $450, and $550 respectively. The question is it a good investment? And how do we value this project or this firm? The key issue is that we need to compare cash flows at different points in time. The timing of cash flows matter. For example, if I offer you money 1 year from now and the same money now, the money today is more valuable. The $100 that you receive today is worth more to you than the $100 you will receive 1 year from now. Why is that so? If you get money today, you can invest it and have interest rate over the period. For example, the $100 today could be invested, and depending on the interest rate over the year, at the end of the year, you can get more money. How much interest rate should you ask for agreeing to invest your money? You should ask at least the risk-free rate of return. Currently, it's quite low, about 1%, but it changes depending on economic conditions. So how much would be $100 worth 1 year from now? Suppose that we are able to earn interest rate of 10% per period. We denote by P, $100. P stands for present value. This is the amount of money we have today. The question we are asking, how much money we can create out of this $100 today, given that we can earn 10% interest rate in the future? If we can invest only for 1 period, the amount of money we can get after this 1 period is 100 multiplied by 1.01. 1 is the principal that we invested, and 0.1 is 10% interest rate converted into decimals. So in our example, next period, we can receive $110. Present value. How much $100 1 year from now are worth to you today? So in fact, we are asking the question which is the reverse or the opposite of the question in the previous slide. Again, let's assume that the interest rate is still 10% per period. Using our notation, we are looking for P, the value of the $100 that we receive 1 period from now. F, our future value, is equal to 100. The answer is it's 100 divided by 1 plus 10% interest rate. Again, I start with the same equation, but I solve this equation for P instead of F. So the amount of money I will pay today for $100 1 year from now is $90.91, assuming that I could earn 10% of interest on my investment. The key takeaway from this exercise: the present value is the market price of the future cash flows discounted at the given interest rate. You can also think of it as the amount of money you need to invest today in the best possible investment alternative available to you to generate some future cash flow. What if you have more periods? For example, how much $100 worth 2 years from now? We are looking for future value 2 periods from now. Well, what do? We already know how to calculate future value 1 period from now. So we assume that we invest this entire amount for 1 more year. In other words, again, we multiply by 1.1. Assuming 10% interest rate remains for the second period as well. After we do our calculation, we learn that the future value of $100 today, 2 years from now, is $121. You do not just get $120, meaning like $10 of interest in year 1 and $10 of interest in year 2. You earn $1 more than $120. Where does this additional money come from? It comes from compounding of interest. Notice that for the second year, you earn 10% interest, not on the $100, but on the entire amount of $110. So you are earning interest on interest. How do we answer the opposite question about finding present value of some amount given in the future if you have many periods? For example, how much $100 2 years from now would be worth to you today? Using our notation, we again assume that interest rate is 10%. We are looking for P, value today, or present value, of future value equal to $100. To get this $100, we will invest P now for 2 periods, and each period we will earn interest rate of 10%. So if we solve this equation for P is equal to 100 divided by 1.1 to the power 2. And we can see that this amount is less than $100, of course, but also less than the value of $100 in year 1. That was $90.91. And now $100 in year 2 is worth to us only $82.64. We can interpret this amount as the amount of money you would be willing to pay today for the asset or the project that will pay $100 2 years from now, assuming that this asset or this project deserves 10% rate of return per period. So how do we find present value of the future amount? What will help us here is to introduce the notion of the discount factor. The discount factor tells you how much $1 received T periods from now is worth today. Equivalently, it tells you today's price of $1 received T years from now. This is the formula that summarizes the same exact definition in mathematical terms. Discount factor of time t is 1 divided by 1 plus interest rate that I receive over this entire period raised to the power t. Let's consider another example. Suppose that the interest rate is still 10% and we want to find out the value of $1 received 3 years from now. That is exactly the discount factor 3, and it is equal to 1 over 1.1 to the power 3. The answer is approximately 0.75. Each dollar received in 3 years is worth to me today about 75 cents. I would be willing to pay 75 cents for each dollar that I will receive at time 3. What if this amount is not $1, but $5? The $5 received 3 years will be worth to me approximately $3.76. And how did we calculate this amount? I took $5 and multiplied by the discount factor, or equivalently divided $5 by 1.1 to the power 3. We can create a visual representation of time value of money. In fact, what we are doing, we are sort of moving the cash flows along the timeline. To move cash flows from present to the future, we need to multiply by 1 plus r, raised to the appropriate number of periods. For example, to move cash flow from time 0 to time 2, it is multiplied by 1 plus r to the power 2. To move the same cash flow to the time 4, we multiply this cash flow by 1 plus r raised to the power 4. Or generally, we will multiply the cash flow by 1 plus r raised to the power t. The opposite is done when we want to find the present value of the cash flow received sometime t in the future, and we want to find the present value of this cash flow today. So for example, if this cash flow is received at time 1, we multiply the cash flow by discount factor 1, or 1 over 1 plus r to the power 1. If you are interested in the value of the cash flow received at time 2, we will multiply this cash flow by discount factor 2, which is 1 over 1 plus r to the power 2. If it's the present value of time 4 cash flow, it's multiplication by the discount factor 4, or 1 plus r to the power 4. In general, if we want to find the present value of the cash flow received at some time t in the future, we need to multiply this cash flow by the discount factor t, or equivalently, divide this cash flow by 1 plus r raised to the power t. More generally, you can move cash flows between any two periods. So here is an example. For instance, I know that I will receive $100 2 years from now. I want to invest this amount for 2 more years, and I want to know how much money I will have at time 4 from this investment. There are 2 periods between time 2 and time 4. So to find the future value of the cash flow received at time 2, I simply need to multiply it by 1 plus r raised to the power 2. What if I want to do the opposite? What if I know that I will receive cash flow equal to $100 this time at time 4, and I want to know how much this cash flow would be worth at time 2? Again, there are 2 periods between 2 and 4. So I simply discount my $100 of time 4 cash flow by 1 plus r raised to the power 2. What if we have many cash flows? For example, we have an asset that pays the following cash flows over 3 years. I can't just add these cash flows because they are received at different points in time, but I can add their present value. To find the value of this cash flow stream of 3 cash flows today at time 0, I need to discount each cash flow by 1 plus r raised to the power t, and t is the time period when I receive this cash flow. So assuming that the interest rate in this example is 10%, this is how I calculate present value of each of these 3 cash flows. The first one is discounted by 1.1 to the power 1. The second one, because it's time 2 cash flow, discounted by 1 plus 1 to the power 2. And the third one, because it's time 3 cash flow, is discounted by 1 plus r to the power 3. The value of this project today is $244.93. Why can we add these present values? Because these present values are equivalent of time 0 cash flow. So they are all at the same time, time 0. And this is the reason why I can simply add discounted value. Let's consider a simple leverage buyout example. Suppose you are evaluating a potential leverage buyout, and the projected cash flows are 1 year from now, you potentially receive $0.2 billion, 2 years from now, $0.3 billion, and 3 years from now, $0.35 billion. Assume that you can sell the firm for $1.8 billion at the end of year 3. This is so-called terminal or exit value. And assume that the right discount rate for this particular firm is 15%. What is the largest amount that you would be willing to pay to buy this firm? How do we solve this problem? Here is the solution. We need to discount the cash flows of this deal at 15%, and we take into account time value of money. In other words, the discount factor for each cash flow. The first year cash flow would be discounted by 1.15 to the power 1. The second year cash flow by 1 0.15 to the power 2. And the third year cash flow, which consists of terminal value as well as $0.35 billion, is discounted by 1.15 to the power 3. The final answer is 1.81. This is how much money you will be willing to pay for this firm, $1.81 billion. Note that if we invest this amount today at 15% interest rate, we are able to exactly replicate the cash flows of this firm. This is what I mean. Suppose that at time zero, I invest $1.81 billion at 15% interest rate. In year one, this investment will produce $2.0815 billion, out of which I withdraw 0.2 billion to replicate the cash flow at time one. The rest is invested, again at 15%. In year two, my investment of $1.8815 billion earns 15% interest rate and produces $2.1637 billion, out of which I withdraw 0.3 billion, again to replicate the cash flow of the firm at that time. The rest is again reinvested at 15%. $1.8637 billion invested at 15% produces 2.15 billion. I withdraw this amount, which is exactly equal to 1.8 billion of terminal value plus 0.35 billion of cash flow from this firm, and we are left with zero. So you can see that if I am able to invest at 15%, the amount of money I am willing to pay for this firm, $1.81 billion, would exactly replicate the total stream of cash flows that this firm entitles me to. Now let's talk about the concept of net present value. Net present value is the present value of firm's cash flow net of the costs. This is the typical equation to calculate net present value, and usually the costs happen at time zero, but not always the case. In this formula, C with the index I stands for the cash flow in period I. R is the interest rate that we earn on this project, which is the same as the interest rate we earn on comparable investments. And we record costs as negative cash flows or cash outflows, and we record the revenue as positive cash flows or inflows. So here's an example. Let's go back to our LBO and suppose that you will have to pay 1.6 billion for this transaction. What is the NPV? The net present value of this leverage buyout is then $1.81 billion that you would be willing to pay for this firm, minus the cost that you actually paid, 1.6 billion. So the NPV is positive and is equal to $0.21 billion. So net present value is the value created in today's dollars. This is a profit you earned on your investment, taking into account the time value of money or the opportunity cost of spending money on this particular investment as opposed to comparable other investments. The typical NPV exercise would proceed as follows. You will need to create a timeline. Timeline is a very helpful device to deal with the time value of money, to calculate present values or future values, especially for complicated investments with multiple cash flows. So what is this? The first row in the timeline is number of the time period. So 0 represents present time or now. And then I number the periods as 1, 2, 3, consecutive numbers. And these periods could be years. If I get annual cash flows, it could be months if I get monthly cash flows, or anything else. The second row is dedicated to the cash flows. Notice I carefully distribute these cash flows according to the time when they are received. For example, for this project or this investment, I need to pay $1,000 today. And if I pay this $1,000, I'm expecting to receive $250 at time 1, $350 at time 2, $450 at time 3, and $550 at time 4. The discount factor on this particular investment is 10%, and this is given. Using this 10%, I can calculate discount factor for each period. For example, time 1 discount factor is 1 divided by 1.1, and this is 0.909091. The second discount factor is 1 over 1.1 raised to the power 2, and this is approximately 0.8264. The third discount factor is 1 divided by 1.1 raised to the power 3, and this is approximately 0.7513. And finally, discount factor 4 is 1 divided by 1.1 to the power 4, and this is approximately 0.683. If I multiply each cash flow by the corresponding discount factor, I find present value of these cash flows. So, for example, the present value of $250 received at time 1 is $227.27. The present value of $350 received at time 2 is $289.26, and so on. I found present value of each cash flow in this row 4 of my table. We know that these present values are additive because they are all time 0 values. So when I add all the cash flows, you can use sum function. In Excel, I receive the final answer of $230.28, and it is positive. So the NPV of this project or this investment is $230.28. That means that in present value term, the future cash flows of the project are larger than the $1,000 that I have to invest into it. It also means that I earned economic profit on this investment. This investment increased the value of my portfolio, or if it's a project, the value of the company which I manage, by $230.28. Now, where these cash flows come from? These cash flows come from carefully evaluating accounting data, starting from sales, subtracting costs, and so on, something that we are going to do in later lectures, and something that you probably did in the accounting course already. So you end up with this final, what's called operating cash flows, which you later discount. Now, be very careful with using Excel formulas for this. There are formulas that calculate net present values or present values in Excel, and they're built in, but they have certain timing conventions. So to be sure that your timing conventions are exactly those that you want them to be, it probably is easier to discount cash flows by yourself. That way you exactly know what you are doing. What would happen if discount rate decreases? For example, let's take our previous investment and calculate what happens if discount rate changes from 10% down to 5%. We do exactly the same procedures as we did in the previous slide. We first find discount factors. Notice each discount factor is worth more now if discount rate is lower. For example, our first discount factor with 10% interest rate was slightly more than 0.9. The discount rate with 5% for the same time period is 0.95, which means each dollar received at time 1 is worth slightly more than 95 cents, given that the interest rate we can earn over this period is 5% as opposed to previously earned 10%. And like that for each cash flow in this example, so you can see that the net present value increased. It increased to $396.77. So the fall in the discount rate increases net present values. This is not surprising if we look at the equation which defines net present value. The cost times zero cash flow and the negative one doesn't depend on the interest rate. It's not discounted because it's already present time cash flow. Each other cash flow is discounted by 1 plus R. And this is the number greater than 1. So, by dividing by 1 plus R by the number greater than 1, the value of each cash flow is reduced. The higher the interest rate, the further this number is away from 1. The lower the interest rate, the smaller this number is, the closer it is to 1. So, by dividing each cash flow by 1 plus R, the bigger the R, the smaller will be the result of each of these fractions. I can see this effect more and more when the cash flow is received further and further in time. And this is because 1 plus R is raised to the power t, which produces larger and larger denominator in this fraction. So by looking at this equation, we can see that when R goes up, the result will decrease for the typical project. And by typical project, I mean that our first cash flow comes at time 0, it's the cost, and our subsequent cash flows are generally positive. Can projects have negative NPV? Let's look at the example. And this is the real example. In September 2005, eBay bought Skype for $3.1 billion. eBay stock immediately fell by 4% on the day that this deal was announced. On October 2007, eBay admits it overpaid for Skype by the estimated $1 billion. In September 2009, and this is 4 years later, eBay sells Skype, but notice, it sells Skype for $2.75 billion, which is less than $3.1 billion that it paid for this company 4 years earlier. How much did eBay overpay, knowing what we know now? Let's make a few assumptions. The discount rate for this transaction is 15%. And it's an interesting question how this particular discount rate is determined in real life. We will talk about it later in the course, but it depends on the risk of the investment, in particular on the risk of Skype to eBay, as well as on the comparative investment opportunities for eBay. Let's also assume that cash flows from years 2005 all the way to 2009 were all 0. First, we need to discount the sale price which was paid for Skype in 2009 back to 2005. We divide the sale price of 2.75 billion by 1.15 raised to the power 4. It is equal to 1.57 billion. In other words, in terms of 2005 dollars, eBay received 1.57 billion for the sale of Skype in 2009. The net present value of this deal is negative because the revenue from the transaction is less, it's 1.57 billion, than the cost of the transaction, which was $3.1 billion in 2005 year terms. The NPV of this deal for eBay was negative $1.53 billion. So it is not surprising that eBay's stock fell, lost value upon announcement of this transaction. How would the situation change if during the time that eBay owned Skype, Skype produced 250 million of annual cash flow each year? Again, we would calculate present value of this cash flow back to 2005 dollars. And so here is the discounting of these cash flows. The cash flow stream would produce additional $0.71 billion in 2005 dollar terms. However, NPV is still negative. To conclude, we will consider special formulas. They are shortcuts, they make your life easier, and they are useful in many valuation exercises that we are going to perform. And these formulas are regular perpetuity or level perpetuity, growing perpetuity, and regular annuity. Let's start with perpetuity. It's an infinite stream of identical cash flows. So here's a timeline representing perpetuity. And you can see that starting at time one period from now, I will receive $C each period from this investment, and that would last forever. Now, there are few more assumptions we need to emphasize in order for us to use this formula. In particular, we assume that the interest rate R remains constant forever. If the interest rate changes somewhere in between, for example, after 5 years, the interest rate drops, we cannot use this formula directly, we have to adjust the formula. But assuming that the interest rate stays forever, the cash flows remain the same forever, the present value of perpetuity is equal to C over R, because the infinite sum of terms like this is exactly equal to C over R, and all we need to do is some simple algebra to show it. Growing perpetuity. It's also perpetual or infinite cash flow stream, and the interest rate R is also assumed to stay the same over the entire life of this perpetuity, which means forever. The difference with regular perpetuity is that cash flows are not the same every period, but they grow at the same constant rate. So G stands for the growth rate. Assuming that we start with the first cash flow equal to C, the time 2 cash flow will be C multiplied by 1 plus G, 1 plus growth rate. The time 3 cash flow would grow for one more period, so it will be C times 1 plus G raised to the power 2, and so on and so forth. And again, we don't need much more than algebra to show that this infinite summation of cash flows that grow at the constant rate G and are discounted by using the constant discount rate R is simply equal to C divided by R minus G. Please make sure that you made realistic assumptions about growth rate. Check that growth rate is less than the rate of discount R. If it is not the case, you cannot use this formula. Mathematically, it's clear why it is so, because the result is going to be negative, and that would make no sense because you have a cash flow stream that grows at a very high rate, and yet you get negative present value. So that is just mathematically, but it makes no sense economically as well. Why it makes no sense? It is because you assume unrealistic rate of growth. While rate of growth can be very high for some firms for some periods of time, usually for young firms, they sometimes can double their cash flow streams for, let's say, 5 years. It is unrealistic to assume that any firm could grow at such high rate forever. Typically, after the period of abnormal growth, the growth rate will decrease and usually approach industry average, which is less than the rate of discount. Suppose that the firm 3PAR has expected cash flow next year, which is equal to $100 million. What is the value of this firm if its growth rate is 10% and the discount rate is 15%? So please notice that our growth rate G is 10%, which is less than our discount rate R, which is 15%. Apply growing perpetuity formula. Now we substitute numbers that are given in this example, and the answer is $2 billion. So 3PAR is worth now $2 billion. What will happen if the growth rate is lower? If, let's say, we made a mistake by saying that the growth rate is 10% and it is actually only 6%. Well, again, we apply growing perpetuity formula. This time we substitute 0.06 for the growth rate, and we can see that the value dropped to $1.1 billion, which is quite significant. So when we value growing firms, it is important to carefully and accurately estimate growth rate of cash flows, because small changes in this growth rate, up or down, will affect valuations. In particular, if we overestimated growth rate, we overpay for the company. If we underestimate growth rate, we underpay. Our next special formula is that for the annuity. It is very similar to regular perpetuity, but the cash flow stream is finite. It's not forever. I receive equal cash flows for T period. At time T plus 1, I don't receive anything. And after that time, all cash flows are going to be 0. This sum of T discounted cash flows is equal to the following formula. C over R multiplied by 1 minus 1 over 1 plus R raised to the power T. This is present value of annuity formula. And we can give a lot of examples where this formula is going to be very useful. For example, all mortgages, fixed rate mortgages, car loans, student loans, everything where you should pay the same cash flow period by period is an annuity. And you can use this formula to find the present value of this annuity, the cash flow that you are going to pay, or whatever the question might be. Again, the assumptions here are that cash flow does not change and that interest rate does not change. So as long as this annuity keeps paying its cash flows, the interest rate remains the same. Let's return to our Skype example. This version where there were 4 equal cash flows of 250 million each, and the interest rate is 15%. So this cash flow stream of $250 million for 4 years is an annuity, and we can apply annuity formula to find the present value instead of discounting 4 individual cash flows. Formula and discounting individual cash flows produces, of course, the same result. Suppose that in 2008, Tom took out $153,724 mortgage to buy a house, and he promised to make 30 annual payments. In reality, of course, he will make monthly payments, but for the sake of the example, assume that these payments are annual, once a year. So he is paying $10,000 per year. The following day, he loses his job. The bank lowers his annual payment to $8,000 from $10,000. Suppose the bank wants to sell the mortgage. How much will it get if the appropriate discount rate for this particular mortgage is 5%? Solution. The bank can sell this mortgage for the amount equal to the present value of all the cash flows that Tom will pay to the bank. And these cash flows are always the same. $8,000 every year for 30 years. Again, go back to the annuity formula and see how we plug numbers from the problem into the formula. C is equal to 8,000. R is 5%. Number of payments is 30 in this example. The present value of this mortgage is $122,980. Word of caution about all of these formulas. Formulas are like robots. They always do the same thing. And all these formulas, regular perpetuity, growing perpetuity, and annuity, can be used without any adjustment if you need the present value 1 year before the cash flows start. So if your cash flow starts at time 1 and you apply the formula without any adjustments, you will find present value at time 0. But what if your cash flow starts in year 5, as in the next example? So suppose that this firm 3 par that we already valued expects to get the cash flows beginning 5 years from now. So remember, it's perpetual stream of payments starting in this example 5 years from now. Discount rate is 15%, growth rate 10%. So we apply growing perpetuity formula right here. And the first cash flow that we use in this formula is time 5 cash flow. Formula produces the result, and this is the same $2 billion. But now this is time $4. This is how much this firm would cost if we bought it at time 4 years from now. It's not the amount this firm will cost if we buy it today. Again, the first cash flow starts at time 5 and the resulting PV is indexed by time 4. So how do we convert now present value of time 4 to present value at time 0? We need to discount. So present value of time n would be discounted using discount factor of that time n. In our example, this is time 4 present value. So we will discount by 1 plus r, 1.15, raised to the power 4. In our example, 3 par will be worth now $1.4 billion. And that value was calculated using two-step procedure. First, we applied growing perpetuity formula to find present value at time 4. And then we took present value at time 4 and discounted this value from time 4 to time 0 using our regular discount factor approach. And then I need to take this result and discount time 4 present value to time 0. If you receive some cash flow right now, it will not be counted by the growing perpetuity formula. So what do you need to do? Calculate time 1 cash flow, unless it's already given to you. But then you need to add time 0 cash flow separate. For example, what if the firm will pay $100 at time 0 and consequently will grow at 10% per year? Well, then the time 1 cash flow, which will go into growing perpetuity formula, is 100 multiplied by 1.1. We use $110 million in the growing perpetuity formula because this is our time 1 cash flow. And we divide by R minus G as before. But please do realize that this entire fraction gives us present value of all cash flows from time 1 to infinity, but time 0 cash flow is not included. I simply have to add it separately. The result is $2.3 billion. To summarize, whenever we need to value a firm or a project or a financial asset, future cash flows need to be discounted to find their value relative to dollars today or to find their present value. This process of discounting accounts for the opportunity cost, the cash flow we could generate it if we had taken our next best alternative investment. There are certain formulas we can use to speed up our calculations. We consider 3 of them: perpetuity, growing perpetuity, and annuity. When you use these formulas, be careful